Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Crystal Structure from the paper Functional Materials. Main points which will be covered in this module are: first, a brief review of the structural aspects of materials, which are very important to appreciate the correlations between the materials' crystal structure, anisotropy, and properties. Second, point lattice, unit cell, and Bravais lattices. Third, a comparison between a primitive and a non-primitive unit cells will be discussed in detail. Lastly, various symmetry elements underlying a point lattice have been discussed. So students, let us start with a brief introduction. While bonding between the atoms, which is very critical in defining the basic character of materials, the packing of atoms in the space is also equally important from the perspective of functionality of materials. If atoms are regularly spaced in space, then they form crystalline solids with specific crystal structure depending on the arrangement. Even in crystalline form, if some order with specific directionality prevails over larger length scales, then such material forms are called as single crystals. On the other hand, if tiny crystals they are randomly oriented with respect to each other and have a very sharp boundaries between them, then material formed is called as polycrystalline. In contrast, if there is a lack of long range ordering or arrangement of atoms, it gives rise to amorphous or semi-crystalline structures which exhibit different functional behavior. In this lecture, we will briefly review the structural aspects of materials, which are very important to appreciate the correlations between materials' crystal structure, anisotropy, and properties.
Point lattice. Here we will be discussing what is a point lattice. In general, lattice is an array of imaginary points in space. A lattice is a point lattice if it is a mere collection of points in space such that each point has an identical surrounding when viewed in a particular direction. As you can see from the figure, on left hand side you are seeing a no regular arrangement, whereas on the other side there is a regular arrangement with identical neighborhood. So, a 3D translationally periodic arrangement of points in space is called as a lattice. This figure shows the example of a point lattice where there is a periodic array of points in the space with each point having identical neighborhood. As you can see from the figure that the horizontal separation between the points is represented by A, and the vertical separation by B. These two figures shows the difference between the point lattices. The left figure is not a point lattice, whereas the right figure is a point lattice. Unit cell. We will be discussing about what is a unit cell. Corresponding to the periodicity of a point lattice, we choose three vectors, not all in the same plane. Then, position vectors for all the lattice points are of the form R vector is equal to n1a1 plus n2a2 plus n3a3, where n1, n2 and n3 are the integers. The vector set a1, a2 and a3 then describes a cell which, when translated in space, fills up all of it. This cell is called as a unit cell. There is no unique choice of a unit cell. The only requirement that its translation should reproduce the lattice and fill up the entire space. For example, as evident from the figure, it shows a point lattice and there are several unit cells, all equally legitimate. However, once a unit cell is chosen, it is characterized by a set of parameters called as unit cell parameters. So now to conclude that unit cell is the smallest repeatable unit. Unit cells in 3 dimension. For a 3-dimensional unit cell, the parameters are called as A, B and C, which are related by angles alpha, beta and gamma as evident from the figure. Now let us discuss about a lattice vector. As we have discussed already that many unit cells can be formed by as shown by cell vectors. So we can represent the lattice vector as R is equal to n1a1 plus n2a2 plus n3a3. So lattice parameters are usually defined as the lattice translation vectors and by the angles alpha, beta and gamma. Now before discussing about the lattice systems, let us first conclude or summarize the unit cell. As we have discussed already that unit cell is the most common repeatable unit of a lattice or the smallest repeatable unit of a lattice. So the figure shows the most common shape of a unit cell is a parallelopiped with lattice points at the corners. A unit cell may be of two types, primitive unit cell and non-primitive unit cell. A primitive unit cell has lattice points only at the corners, whereas a non-primitive unit cell has lattice points at the corners as well as some other points are there. Now, the example of a non-parallelopiped primitive unit cells are Wigner seeds unit cell and Brillouin zones. The classification of unit cells. By changing the magnitude of the three vectors, that is A1, A2 and A3, and the angles between them, there are 7 types of unit cells, or we can say 7 crystal systems, that is cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic. Now these 7 crystal unit cells or these crystal systems are represented by 14 Bravais lattices. As we have already discussed that the crystal systems in 3D are of 7 types, that is cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, which is also known as trigonal, and hexagonal. These unit cells have lattice points at the corner and they satisfy the conditions of a point lattice. However, it is possible to place additional points in these 7 unit cells and still have a point lattice. For example, a point lattice is obtained by putting an additional lattice point in the center of a cubic lattice or at the center of the 6 faces. These are familiar body-centered cubic and face-centered cubic structures. So depending upon this classification, we have 14 Bravais lattices. 14 Bravais lattices. In 1848, a French crystallographer showed that there are exactly 14 possible point lattices. These are also called as Bravais lattices. Thus, the terminology point lattice and Bravais lattices are synonymous. This figure shows all 14 point lattices. These are called as conventional unit cells as they show the symmetry of the lattice well. But again, it is not necessary to select a unit cell only in this particular way. As shown in the figure that a cubic lattice system has all the sides, that is A equal to B equal to C, and all the angles, that is alpha, beta and gamma, equal to 90 degree. And it exists in simple cubic, body-centered and face-centered structure. Next is tetragonal. Tetragonal, in this, A is equal to B and it is not equal to C, whereas all the angles are equal to 90 degree. It has only simple and body-centered structure. Next is orthorhombic. Orthorhombic has all the sides to be not equal to each other, that is A not equal to B not equal to C, whereas all the angles are equal. It exists in simple and body-centered. Rhombohedral has all the sides equal, but all the angles, that is alpha, beta and gamma, they are equal but they are not equal to 90 degree. Rhombohedral is the one, whereas orthorhombic exists both in simple, body-centered, base-centered and face-centered. Next is hexagonal. Hexagonal has A equal to B but not equal to C, but alpha and beta, they are equal to 90 degree, whereas gamma is equal to 120 degree. Monoclinic has all the sides not equal to each other, but alpha is equal to gamma is equal to 90 degree, but not equal to beta. Whereas triclinic has all the sides not equal to each other, that is A not equal to B not equal to C, and all the angles are not equal to 90 degree and not equal to each other also. Motif and crystal lattice. Motif can be defined as a unit of pattern. For a crystal, it is an atom, a group of atoms, or a formula unit, or a set of formula units oriented in different manner with respect to each other as shown in the figure. Motif is also called as bases at times. When motif is combined with a point lattice, what it gives rise to is called as a crystal lattice. That is, a crystal structure is equal to point lattice plus motif. If there are more than one formula present in a unit cell, and if all of them were identically oriented, then the unit cell would be non-primitive. However, there are several occasions when you may have more than one formula unit present in a unit cell, but still the unit cell is primitive. In such instances, the formula units are oriented in such a fashion with respect to each other that a group of formula unit makes up one repeatable unit. Cell contains only one dog. However, in the picture on the right, one dog is standing up whilst other is oriented downwards. Hence, to make a repeatable unit cell, one needs to consider one dog of each type lying next to each other. Primitive versus non-primitive unit cell. In a primitive unit cell, it consists of one lattice point per unit cell, and in a non-primitive cell, we have more than one lattice points per unit cell. Now we can represent the volume of a non-primitive cell as number of motif multiplied by the volume of a primitive unit cell. Now, one lattice point may contain one or more than one formula units of type of atoms depending on how they preserve the definition of a lattice. Crystal systems and Bravais lattices. This table represents the 7 crystal systems and the different types of Bravais lattices corresponding to crystal systems. As we can see from the table that the cubic crystal systems has 3 corresponding Bravais lattices. P corresponds to simple or primitive, I to the body centered, and F for the face centered, and C for the end centered. All the 7 crystal systems exhibits the primitive Bravais lattice, whereas the body centered exists for cubic, tetragonal, and orthorhombic. Face centered is in cubic and orthorhombic, whereas end centered exists for orthorhombic and triclinic crystal systems.
Symmetry in crystals. So students, let us discuss what all kinds of symmetries exist in crystals. There are various symmetry elements underlying a point lattice. These are: first is reflection, rotation, inversion, and lastly rotation and inversion.
Rotation and reflection. First, we will discuss about the rotational symmetry. This kind of symmetry is about an axis. When a lattice is rotated about this axis by an angle 360 degree by n, some arrangement of lattice points is reproduced. This axis is called as n-fold rotation axis. Possible values of n are 1, 2, 3, 4 and 6. but not 5. As evident from this figure that we have four-fold axis, that is M1 goes to M2, M3 and then M4. For three-fold axis, M1 goes to M3, two-fold axis, M1 goes to M4. Next is reflection. This kind of symmetry is about a plane. That is, if there is a mirror plane such that one half coincides with the other half as mirror reflection. These are some of the examples of rotational symmetry along with the symbols which are generally used to depict the type of rotational symmetry element. Inversion and rotation inversion. First, we will discuss about the inversion. A point is an inversion center if every point on the lattice reproduces another lattice point equidistant from the inversion center on a line joining these two lattice points and also passing through the inversion center. Now, as we can see from the figure that there is an inversion center at the center and M1 becomes M2. Next is rotation inversion. This symmetry operation is a combination of rotation and inversion. That is, a lattice is reproduced when it is given n-fold rotation and then it shows the inversion symmetry. Now as we can see from the figure that M1 becomes M1 prime due to four-fold rotation and then inversion takes from M1 prime to M2. Lattice symmetry. The lattices typically have the following symmetry elements as shown in the figure also. First is translational symmetry, second rotational symmetry, and third is reflection symmetry.
Now let us discuss about the point and space groups. First, we will discuss about the point group. The group of all symmetry elements of a crystal except the translations, example rotation, reflection, etc. is called its point group. There are 7 point groups for a point lattice, 32 point groups for a crystal lattice. Now students, let us start with the space group. What is a space group? The complete group of all symmetry elements, including the translation of a crystal, is called its space group. There are 14 space groups for point lattice and 230 space groups for a crystal lattice.
For example, the minimum symmetry condition of 7 crystal systems is shown in the figure. According to this, a cubic system has 4 three-fold rotation axes and this forms the minimum requirement. Now we return to why non-primitive lattices are chosen in Bravais lattices. The reason behind it is that a non-primitive cell such as face-centered cubic cell has higher symmetry than the primitive cell built in it as FCC unit cell and has 4 lattice points, implying that it has 4 primitive unit cells. Likewise, the reason why we don't have a face-centered tetragonal cell, it is because we can always have a smaller unit cell inside, which is a body-centered tetragonal and with similar four-fold symmetry.
So students, let us summarize what we have learned in this module. First, a structure is made up of a point lattice and a motif. Second, a point lattice is made of a regular repeating units of cells which are called as unit cells, or we can say that a unit cell is the smallest repeatable unit. The repeatable unit is bigger in case of non-primitive lattice. Third, symmetry determines the crystal systems and crystal lattices. Fourth, there are total of 7 crystal systems and 14 Bravais lattices. Thank you.